Hi, I'm back. The area of the curve that a person is allowed to, where a person is allowed to reject the null hypothesis, is actually has a name. It's called the rejection region. And in a one, it's the area beyond the critical value that contains the combinations of people that will end up giving the researcher a high enough test statistic to reject the null hypothesis. And in a one-tailed test, a person actually can only use one of these two areas as the rejection region. If the person plans ahead of time to use the positive critical value with 5% to the right of it, the person's rejection region in that case is actually only this area above the critical value. So a person who's planning ahead of time to do a one-tailed test and to use the positive critical value, their outcome, they can only reject the null hypothesis if their outcome ends up in this area above, equal to, or above the positive critical value. This is their only rejection region. They can't reject if they end up down in this area below the negative critical value. So, and then if the person plans ahead of time to do a one-tailed test with the negative critical value, the person's only rejection region is actually this area down here with data sets that have t-scores equal to or below the negative critical value. And when a person does a one-tailed test and decides to use a negative critical value, if the person's data set ends up equal to or below the negative critical value in this rejection region, the person can reject. But if the person was planning to use this negative critical value and the person's data set ends up here at the upper end of the curve, the person can't reject up here because the person decided ahead of time to only use one goal area or one rejection region down here. So in a one-tailed test, the total area of the curve that's in the rejection region is actually only 5%. Only 5% of the curve is the rejection region, because in a one-tailed test, your rejection region is either up here, either down here if you plan to use the negative critical value, or up here if you plan to use the positive critical value. It's like you're on a team that can only score at one end, and you only have one goal area. That's actually why it's called a one-tailed test. In a two-tailed test, you're allowed to reject the null hypothesis if you make it down into this area below the negative critical value, equal to or below, or if you make it, your outcome ends up in this area with a t-score equal to or above the positive critical value. So you can actually reject in either area. If you end up down here, you can reject. If your t-score ends up here, you can reject. So it's like a team that can score at either goal area. But there's a penalty for having two goal areas like this. When you're allowed to reject at either end of the curve, your rejection region has to be cut in half at both ends. Because typically the maximum total area of your curve that can be in the rejection region is 5%. So if you want to use both rejection, if you want to be able to use either rejection region, you have to cut this in half so that the total rejection region, the sum of the two shaded areas, doesn't go over 5%. And in a one-tailed test, you don't have to worry about the total rejection region going over 5% because you're only using one end of the curve. So in a two-tailed test, it's like you're taking your one rejection area, cutting it in half, and putting half of it down here at the left end and half at the right end. And why can't the total shaded area be more than 5%? If the total shaded area is more than 5%, then it becomes too easy to reject the null hypothesis, because if too much of the curve is shaded, it becomes too easy to get an outcome inside of the rejection region. Let's see what so the total rejection region in this one-tailed test is 5%. Because even though I'm showing a 5% rejection region down here and a 5% rejection region up here, in a one-tailed test, only one of them can actually be used. A researcher has to plan ahead of time which one they're going to use, just like how a team has to decide ahead of time which goal area, which end of the field they're allowed to score at. So the total rejection region is 5%. And in the two-tailed test, you're dividing your rejection region in half and putting half of it down here and half of it up here. So it's like a team who decides that they're going to make the goal areas at both ends of the field only half as wide, make both of them half the size, and allow themselves to score at either end of the field. It's like a team thinking, we want to score at either end of the field, but that might make it too easy for us to score. So in order to compensate and to make it not too easy for us to score, we're gonna make each touchdown area or each goal area only half as wide. So it's not too easy for us to score when we're allowed to score at either end. So the total rejection region is still 5% in the two-tailed test. So when we went to our critical value table and we went up to one-tailed and looked at 0.05 and we got our critical value, what this gave us, it gave us 1.66. And the reason it says 0.05 up here is because 1.66 is the critical value that has 5% of the curve beyond it. That's why it said 0.05. So in a one-tailed test, it gave us the critical value with 5% beyond it at one area, one end of the curve down here. And if 5% is beyond 1.66 up here, then 5% also has to be below the opposite of minus 1.66 down here, because it's really because both ends of the curve are the same shape. It's symmetric. So if 5% is above 1.66, then 5% will also be below minus 1.66. Let's see what happens if we go to two tails and use 0.05. If you use two tails 0.05, what does it say up in the one-tailed row up here? When two tails is 0.05, one tail says 0.025. So let's see what we get down here in this column. We get about 1.99. When it says one tail 0.025, that means that 1.99 is actually the point that has 2.5% above it at one tail, at one end of the curve down up here. This is, you would call this one tail up here. So this one tail above 1.99 is 2.5%, which is why it says one tail 0.025. But when one tail is 0.025, two tails is 0.05. What that means is that in this curve down here with the two-tailed test, the total rejection region is still 5%. So what it means when it says two tails 0.05 is it means when you add up the area in both tails, meaning you add up the tail above 1.99 and the tail below the opposite, which is minus 1.99 down here, the sum of these two tails comes up to 5%. So one tail above 1.99 is only 2.5%, but two tails added together at the left end and right end adds up to 5%. That's why it says two tails is 0.05, meaning the sum of the two tails at both ends comes out to 0.05. And my laptop is actually going to run out of batteries, so we'll see if I can plug in fast enough. Okay. I also need to explain the p-value. If the p-value is actually different than the rejection region, the rejection region is the area, has to do with the area at the critical value or beyond the critical value. What the p-value is the total area or the percent of combinations that are at the t-score of your sample or beyond it. So what does that mean? This is 1.99, the critical value. If our t-score, imagine our t-score came out to 2.0, actually 2.7. That's in this area that's above the critical value, the positive critical value, so it might be right here. What the p-value will be is actually the amount of shaded area at 2.7 or above. The percent, actually, of the percent of samples that are at 2.7 or above. Basically meaning the percent of samples that will give you a t-score of 2.7, like your sample did, or a higher t-score. And if you're in the rejection region, your p-value is smaller than the rejection region is, because your outcome is beyond the critical value, your t-score is beyond the critical value, and the p-value only includes the percent beyond your t-score. The p-value works differently in a one-tailed test than it does in a two-tailed test. If it's a one-tailed test, it actually only calculates the area beyond your t-score, meaning if your t-score comes out to 2.7 up here in a one-tailed test, the p-value is only has to do with the one tail, one end of the curve, meaning it's just this one, the percent of samples at this one end that are at 2.7 or higher is your p-value. If you end up with negative 2.7 as your t-score down here in a one-tailed test, which is it's further to the left. Negative 2.7 is further to the left of 1.66. It's further to the left of negative 1.66, which is our negative critical value. So it's in this negative rejection region. In a one-tailed test, the p-value is only the area at one end of the curve, which is the percent of samples that will give you a t-score of negative 0.7, or, which is what you found, or further to the left. So the p-value will either be the percent. If you have a positive t-score, it'll be the percent up here. If you have a negative t-score, it'll be the percent down here in a one-tailed test. A two-tailed test works differently, because in a two-tailed test, your p-value is actually at both ends of the curve, meaning if your t-score ends up being 2.7 in a two-tailed test, your p-value will actually be the total percent at or above 2.7 and the total percent at or below the opposite of your t-score, which is negative 0.7 or negative 2.7 down here. I wish I had room to write negative 2.7, but it's just the opposite of 2.7. So this is 2.7, this is negative 2.7. And you actually have to add up the total percent at your t-score and beyond at this end, and the total percent at the opposite of your t-score and beyond down here. And that ends up, the total of those 2% ends up being your p-value in a two-tailed test. And you can reject, if your outcome ends up being inside the rejection region, which is when you're allowed to reject the null hypothesis, your p-value will be 0.05 or lower. And I told you that one way to decide whether to reject has to do with whether you're at the critical value, whether your t-score or test statistic is at the critical value or beyond. Another way to decide whether to reject is to check your p-value and see if it's 0.05 or lower. And those two really go hand in hand, because If you're inside the rejection region, meaning your t-score is beyond the critical value, your p-value has to be 0.05 or lower, because the total rejection region, which is the total shaded area inside this curve, is 5%. And so the total of this black shaded area and this black shaded area is 5%. And if you're in the rejection region, your p-value, which is the orange area, has to be less than 5%, because it's less than the total of the two shaded areas. The total of this orange area over here and this orange area over here is smaller than the total of this black area and the total of the whole black area right here. And the total of the two black areas is the total rejection region, which is 5%. So the p-value has to be smaller than that, because it's not taking up the whole rejection region. And what does it look like? In my drawing, it looks like this is about half of the 2.5% down here, and this is about half of this 2.5%. So the total of these two orange areas would be about 2.5%, which would mean that your p-value would be about 0.025. My drawing isn't accurate, but if you considered my shading to be correct, then the p-value would be about 0.025, which is less than 5%. If we wanted to get the real p-value, we'd have to look it up. Also, when your outcome is in the rejection region down here, your p-value is only a segment of the total rejection area of 5%, meaning this p-value has to be a smaller percent than the total 5%. So once again, if you're in the rejection region, your p-value has to be 0.05 or lower. So having a p-value of 0.05 or lower is just something that goes along with having a test statistic or t-score in the rejection region beyond the critical value, or at the critical value or higher. When there isn't really a table to look at p-values. P-values pretty much have to be calculated with a computer unless you do some advanced math to get the p-value. The critical values can be looked up in a table like we did. But you might wonder, when the computer calculates the p-value, how does it know what percent of samples are in this slice down here that's above the t-score you found? Well, the computer, when it calculates it, the computer knows that you have a t-distribution curve with a df of 99. So the computer says, I know the shape of the curve, and I know where your t-score is. So it can actually use both of those pieces of information to calculate how big of a piece this is right here inside this area of the curve. And since the computer uses the curve to decide what the p-value equals, that means that in order for the computer to give you a correct p-value, in order for it to give you the correct percent that's beyond your data set up here, your data set has to fall under the correct type of curve. Your data set has to fall under a t-distribution curve. Otherwise, the computer won't give you the correct p-value. So it's like if you look at this right here, if your t-scores don't follow the shape of the t-distribution curve, and your t-scores are actually skewed like this, what's going to happen is the computer is still going to assume that you have this t-distribution curve like this. And if your outcome ends up being right here, or let me make this better. If the computer assumes that your outcome is falling under a t-curve right here, and this ends up being your outcome, your t-score down here on the number line, you actually have a pretty big percent of samples that are beyond your t-score up here. But if you ask the computer to calculate a p-value, what it's going to do, it's going to use the curve, and it's going to calculate the percent of outcomes or samples beyond your t-score under the curve, and it's not going to include these up here. So the percent that it gives you is actually not really the percent of samples beyond your t-score in this case. It's not a valid p-value. That's why it's important for your outcome to actually fall. It's important for the possible samples to actually fall under this t-distribution curve. And how can we know if the samples really fall under this curve? How do we know if our outcome is really a member of a set of possible outcomes that fall under this type of curve? Well, there's this is how you would know. One thing that matters is the curve of not t-scores, but the curve goes around the sample means, meaning the shape of the curve that goes around the means of the possible samples. So this is the same combinations that might be selected, but now each one is stacked above its mean instead of its t-score. The sample means have to have a normal shape in order for the t-scores of the samples to follow the t-distribution curve that you need to have. And in one of my later videos, I'll actually talk about the situations in which the sample means will be normal. If the sample means are normal, meaning if our data set, which had a mean of 130, let's say 130 is up here, our data set has a mean of 130 up here. If our data set, our set of data with a mean of 130 is one combination inside of a normal curve of combinations above the sample means, then our outcome, the t-score of our outcome, which was 30, will be one combination under a t-distribution curve. So as long as our sample with a mean of 130 is a member of a normal shape of sample means, our t-score, which was 30, will be a member of a set of t-scores that falls under a t-distribution curve. So these two shapes go together. In order for the t-scores of the possible samples to have a t-distribution curve around them, the possible sample means have to have a normal curve around them. And I'll talk about why that is more in a later video. So basically, you want the sample means to be normal, so you will have a t-distribution curve around the t-scores, and you want to have a t-distribution curve because you have to have that curve, the t-distribution curve, in order for the computer to calculate p-values, in order for it to calculate valid p-values. I hope that makes sense. You can send me any questions if you have any. I'm also going to talk about the independent samples t-test. Basically, in an independent samples t-test, all these rules that I talked about with the t-distribution, these all work the same way. You have the only difference, really, is that you're not collecting just one sample, you're collecting two samples. Oh wait, first I was going to talk about how, in one of my later videos, I'll talk about how when a person does a one-tailed test and plans to use the positive critical value, it's called a right-tailed test. And if the person is doing a one-tailed test and planning to use the negative critical value, it's called a left-tailed test. So a left-tailed test and a right-tailed test are two types of a one-tailed test. So we can already see that in a one sample t-test, there's two different curves that are important. The curve around the t-scores is important because it's used for calculating p-values, and it's also used for determining what the critical values are. And the curve around the sample means is important because its shape determines what the shape of the t-scores will be. That's the reason why it's really important. The sample means have to be normal for your t-scores to have the correct t-distribution shape. Maybe we can talk about an independent sample t-test, which is a two-sample t-test. The purpose of an independent samples t-test is to test whether two populations have equal means. In my example, in the PowerPoints I was saying, it could be used to test if dog owners are taller than cat owners. I think my example was something like that. If we actually wanted to test that, we would have to collect a sample of dog owners and a sample of cat owners. Maybe we recruit a sample of 50 dog owners and measure their heights, and we also recruit a sample of 50 cat owners. and we measure their heights. Our 50 dog owners will have a mean, a sample mean. X bar is what stands for sample mean. Let's say it came out to 57, and our sample of cat owners, the average of those 50 people came out to 52. We also have, we'll end up, our 50 dog owners will give us a standard deviation it'll tell us how spread out they are. Maybe it comes out to 2. Let's say they both come out to 2. The standard deviation of the 50 cat owners, the standard deviation of their heights also comes out to 2. And we have samples of 50, so n is 50 in both of these. Later on, we'll be talking about a sample mean difference, which is basically the mean of the dog owners minus the mean of the cat owners, which would come out to 5 in this example. This is called the sample mean difference, and it comes out to 5. The t-score, if we look at our formula in the PowerPoints, it's the top of the formula is the mean of sample 1 minus the mean of sample 2. On the bottom, you have this right here. Standard deviation of your first sample squared over the number of people, or the sample size of your first sample, which is 50, plus the standard deviation of your second sample, which is still 2 again, squared over the number of people in sample 2, which is 50 again. How can we solve this square root on the bottom? Well, 2 squared is 4, so we actually end up with 4 over 50 plus 4 over 50. If we add up those two fractions, oh sorry, I didn't mean for that to be 40. These two will add up to 8 over 50 if you add the fractions. You add 4 plus 4, and you get 8 over 50. If you divide 8 by 50 with a calculator, you get 0.16. The square root of 0.16 is equal to 0.4. So the entire bottom of our formula comes out to 0.4. So our t-score is 57 minus 52 over 0.4. What does this come out to? 5 over 0.4. Which is 12.5. That's a t-score of our entire data set. So once again, you'll have a curve of all of the possible combinations that could be selected, and it'll be above the t-scores. and there will actually be many, many combinations above. There'll be many, many combinations that could be selected from these two populations. But in theory, you have a stack or a shape of combinations that are stacked above their t-scores. Even though no one will actually create this graph of t-scores. Well, I mean, no one will actually put together all of these boxes of these millions of samples that could be selected. But those samples do have a shape around them, and that shape can be predicted. This is a possible combination of 100, 50 people and 50 people. This is a possible combination of 50 and 50. And each total combination of 100 has a t-score, its own t-score, just like how our combination of 100 had a t-score of 12.5. 12.5 will be way out here somewhere because it's a big t-score. It's actually much bigger than you would ever usually find. But our combination of 100 will be out here, at least in this example. And the curve that goes around these t-scores will actually be a t-distribution curve, just like with the one-sample t-test. With degrees of freedom of, in an independent samples t-test, the degrees of freedom is actually capital N minus 2, which is the total number of people in both samples minus 2. So we have 100 people minus 2, which is 98. So this exact shape right here, outlining the t-scores of all of the possible combinations that are available to be selected, is a t-distribution curve with degrees of freedom of 98. And if we want to know what the critical values are for rejecting the null hypothesis, we can go to our t-table again. We can find our negative critical and our positive critical. All we have to know is our degrees of freedom, just like we did before. Before we had a degrees of freedom of 99. Now we have a degrees of freedom of 98, which are about the same. Which means if we go back to our t-table, what do? If we want the one-tail critical values, we go to where one tail is 0.05, and we go down to where the degrees of freedom are. It doesn't say 99, but 99 is pretty close to 100. So technically you're not supposed to go over your degrees of freedom. That's why last time I used 80. But for this example, I'll just say 1.66 for 100 degrees of freedom. If I give you a homework assignment, I'll make sure to let you know what rule to follow for using this table. So this is saying that in a one-tailed test, in this column right here where one tail is 0.05, 1.66 will actually be the t-score that marks off the upper 5%. And everything above that will be the rejection region. So in my example, our t-score was way above 1.66. It came out to 12.5. So our outcome is actually way into the rejection region. It's somewhere way up here, 12.5. So 12.5 will definitely let us reject the null hypothesis because it's definitely above 1.66. If the positive critical value is 1.66, the negative one would be negative 1.66. That's the negative critical value that has 5% to the left of it. These are the one-tailed critical values. Remember, a two-tailed critical value is whatever critical value has 2.5% beyond it. So let's see what that would be in our t-table. In a two-tailed test, you go to where two-tailed is 0.05, and you go down to our degrees of freedom, which is, we said 100, 1.98. It's about 1.98. So actually, 1.98 would be the point that has 2.5% above it. So it's 1.98 is up here somewhere, and it's up here somewhere. Those are our two-tailed critical values. (1.98) and negative 1.98. And we've definitely reached these critical values too, because we've definitely reached the upper critical value, because we're up here at 12.5. So we definitely could reject the null hypothesis. So these, you can still use the same critical value table and follow the same rules with an independent samples t-test. You can still follow the same rules for using the t-table to get your critical values. You just have to know your degrees of freedom. And you have to know if you're looking at a one-tailed critical value or a two-tailed critical value. The only difference is, under the curve, instead of having one sample, like you did here, like one sample of 100 people, like where each of these is just a group of 100 people, it gives you a t-score. Because here we had a group of 100 students who gave us a t-score. Here you have, in an independent samples t-test, we still have 100 people that give us a t-score, but now it's actually a group of 50 and a separate group of 50. It's 50 dog owners and 50 cat owners that all give us our t-score. And there's always possible combinations of 50 dog owners and 50 cat owners that could be selected when you're sampling from the two populations. So the p-values are calculated the same way. If it's a one-tailed test, the p-value is the percent beyond, at or beyond your exact t-score at one end of the curve. In a two-tailed test, it's actually the percent at and beyond your t-score added to the percent at and beyond the opposite of your t-score. So you add both ends of the curve together to get your t-score. What am I saying? Not t-score. You add both of them together to get your p-value. In a one-tailed test, your p-value is at one end beyond your t-score. In a two-tailed test, it's at both ends. It's the total of both of these areas. It works the same way in an independent t-test. In a one-tailed test, the p-value would just be the percent beyond 12.5 up here, which is our t-score is 12.5. It would be the percent at and beyond 12.5. If we were doing a two-tailed test, the p-value would be the percent at and above 12.5 added to the percent at negative 12.5 and to the left. This percent, it would be this area added to this area beyond, at or beyond negative 12.5. In order for the p-values to be calculated correctly, the possible outcomes have to have the right shape. The set of possible samples in here that our sample is a member of, or I mean, the set of possible combinations that our combination is a member of with these two samples has to fall under the correct type of shape. It has to fall under a t-distribution curve with a degrees of freedom of 98. Otherwise, our p-value won't be calculated correctly. How can we make sure that it actually does follow under this shape or this curve that it's supposed to be under? Well, there's in order to make sure that it does, the t-scores do have that shape, you have to also make sure that the shape of the sample mean of another curve, which is the curve above the sample mean differences, has a normal bell shape. I'll explain that again. I think that I said that a little bit too fast. The sample mean differences are just whatever the top of the t-score equals. In our case, it came out to 5. So our outcome, or our data set, had a sample mean difference at 5. And there's actually each combination of 100 that could be selected for our study has its own sample mean difference, which could be 5 or it could be a different number. So some outcomes will have a sample mean difference of 5. Some combinations will give you this sample mean difference. Others will give you other differences. For example, a data set where the sample 1 has a mean of 57 and sample 2 has a mean of 54, that data set will give you a difference of 3, because 57 minus 54 is 3. So that combination would be above, would be at or above this sample mean difference of 3. Other data sets might give you a different score of 4. In order for this test to work properly, the curve that goes around the sample mean differences has to be a normal shape. Because if the sample mean differences, which is the top of the t-score, has a normal shape, then the t-scores will have a t-distribution curve. It'll have the correct type of t-distribution curve that we want it to. So basically, the top of the t-score, each possible data set has a value for the top of the t-score, and those values have to have a bell curve in order for the t-scores of the possible combinations to have the correct t-distribution curve. And why do we want this t-distribution curve? Why do we want this correct shape right here? You have to have this shape in order to calculate p-values. Just like in our one sample t-test, the sample means had to be normal in order for the t-scores to have a t-distribution curve. And in an independent samples t-test, the sample mean differences have to be bell-shaped in order for the t-scores to follow the t-distribution curve. So you always want your t-distribution curve to be correct. You always want to have the correct shape around your t-scores. And in order to make sure that these t-scores do have the correct shape around them, you have to check whether the sample mean differences are normal in an independent samples t-test. And in a one sample t-test, you have to make sure that the sample means are normal. So let me see if I can summarize this. When the sample means are normal, you have a t-distribution curve around the t-scores. And when you have a t-distribution curve around the t-scores, you get valid p-values. Valid p-values can be calculated. And each of these things leads to the other one. In an independent samples t-test, you have to have sample mean differences have to be normal. If they are normal, you end up with the t-distribution curve that you want to have around your t-scores. Your t-scores will have the correct shape that they're supposed to have. And when the t-scores have that correct shape that they're supposed to have, the computer will give you valid p-values. So when you're doing the test, what you want to do is you want to make sure that this thing right here is true. In a one sample t-test, you want to make sure that your sample means are normal. And how can you know if they're normal? In a one sample t-test, you'll have normal sample means if one of two things is true. If the population being studied is normal, or when data is collected from at least 30 people. In an independent sample t-test, you want to make sure you have normal sample mean differences, and that'll be true if you're sampling from two populations, so if both populations are normal, then the mean differences will be normal. Or if data is collected, if both samples have at least 30 people. And a lot of the time, it's hard to be totally sure if the populations that you're sampling are normal. So, since you're often not sure about whether they're normal, the safest thing to do is to satisfy this other thing, to collect data from at least 30 people, or in an independent sample t-test, to collect data from at least 30 people in both samples. Because if you've satisfied number 2, you don't have to worry about number 1 being satisfied. If your samples have at least 30 people, you actually don't have to worry if you're studying normal populations. You can just go ahead and do your test without even worrying about it. And I think that's enough for this video. I have some other videos that go into more detail about the distributions I've talked about. Basically, in these two types of t-tests, you have two types of distributions that are important. The distribution of possible sample means and the distribution of possible t-scores. Those are the two important distributions in a one sample t-test. T-scores are important. The distribution of t-scores is important because it gives you your critical values and p-values. The distribution of sample means is important because its shape determines what the shape of the t-scores will be. In an independent samples t-test, where did I put it? You have a distribution of t-scores and a distribution of sample mean differences, which has to do with the top of the formula. The t-scores are once again important because they give you the distribution of t-scores under the curve gives you p-values, and it lets you look up critical values. The reason that the distribution of sample mean differences are important is because the shape of the sample mean differences determines what the shape of the t-scores will be. And so when you have an independent sample t-test, you're dealing with these two curves, sample mean differences and t-scores. When you have a one sample t-test, you're dealing with these two curves, sample means and t-scores. And I think that's enough for this video. I think it'll help if you watch some of my other videos that go into more detail about some of these topics.